Well, welcome to this introduction to SPSS. This introduction assumes no knowledge at all, except perhaps knowledge of how to count to 10. This video will not only introduce you to SPSS, but will also impart some basic skills on statistics as well. To begin this discussion, consider the following researcher who wants to explore whether consumption of ice cream improves happiness. He decides to conduct this research because he's interested in happiness, primarily his own, and also wants to justify his obsession with ice cream. To conduct this study, he surveys 20 participants and asks each person to estimate the approximate number of ice creams they consume each year and the extent to which they feel happy on a scale of 1 to 10. He then enters data into a spreadsheet in SPSS as this slide shows. Each row in this spreadsheet represents a different person. One column specifies the number of ice creams each person consumed every year, and another column specifies the extent to which each person feels happy on a 10-point scale. Your task is now to complete this task yourself. I don't mean you should loiter in the street and ask people how many ice creams they consumed each year, because that would be unusual. I mean, enter these data into the spreadsheet. Initially, attempt to utilize your intuition to decide how to enter these data. That is, try to enter the data without instructions. But if you're not entirely sure how to proceed, here is some advice. First, you need to open SPSS. If you can't open SPSS or download SPSS on a computer, perhaps seek advice from your college or supervisor. Someone should be able to help, unless of course everyone has been abducted by an army of lizard overlords, and these lizard overlords use a rival statistical package. Second, simply enter the numbers into the spreadsheet. And third, you should notice two choices at the bottom left of this spreadsheet, data view and variable view. To label these columns, press variable view, and then enter the names of these columns in the left side of this spreadsheet. These names can include any letters, numbers, or underscore, but nothing else. Now, return to data view and scan the two columns carefully. Did you notice a pattern? Did you notice, for example, that high levels of ice cream consumption tend to coincide with high levels of happiness? In contrast, low levels of ice cream consumption tend to coincide with low levels of happiness. In other words, at first glance, these data indicate that ice cream consumption might promote happiness. To depict these data graphically, you could construct a scatterplot similar to this graph. In this graph, each dot corresponds to one person. The dots towards the left correspond to people who consume limited levels of ice cream. The dots towards the right correspond to people who consume significant levels of ice cream. As the dots proceed from left to right, they also tend to rise, indicate that people who consume more ice cream tend to be happier. Your decades of ice cream consumption might have rescued you from unmitigated despair. So how do you generate this scatterplot? Well, to achieve this goal, choose the Graphs menu and then Graphboard Template Chooser to generate the next screen. Highlight the two relevant column labels, ice cream and happiness. To achieve this goal, hold the Shift key down as you click these two labels. At the bottom of this screen, you should choose the option called Scatterplot and then press OK to generate this graph. Now, this scatterplot shows you that people who consume many ice creams tend to be happier. But how strong is this relationship? To what extent can we predict the happiness of someone from the number of ice creams they consume? If our answer to this question is vague, nobody will be especially impressed. But if we refer to some number, such as the correlation between ice cream consumption and happiness is 0.42, people might assume we're some kind of genius, until of course we walk into a poll 2 minutes later. To derive some number that represents the strength of this relationship, researchers often use an index called a correlation. They might even refer to this index as a correlation coefficient to seem really intelligent. So what is a correlation? Well, here are some basic principles. In particular, a correlation is an index or number that ranges from -1 to 1. A correlation of close to 1 indicates that high scores on one measure, such as ice cream consumption, always coincide with high scores on the other measure, such as happiness, as this scatter plot shows. A correlation of close to -1 indicates that high scores on one measure always coincides with low scores on the other measure. Whereas a correlation of close to 0 implies no relationship. High scores on one measure do not necessarily coincide with high or low scores on the other measure. As the number approaches 1 or -1, the relationship becomes stronger. To illustrate, estimate the correlation of this scatter plot. That's a good attempt, unless of course your attempt was 34,627. The correlation is actually 0.62. Note we've used the letter R instead of the word correlation.
How do you calculate a correlation
Researchers
in
tend
SPSS?
to use the letter R to symbolize correlation.
Choose the analyze menu.
Would you like to know
The
why
menu that
researchers
uses
use the
conduct
letter
most
R
statistical
to
tests.
symbolize correlation?
Then about a third of the
Well,
way
I
down,
would. I have
choose
no idea.
correlate and then bivariate to generate this screen. Transfer your two measures, ice cream and happiness, into the box called variables, usually by clicking each label in turn and pressing the right arrow. Finally, press OK. The output looks unnecessarily complex. To uncover the correlation, locate the row that coincides with one measure, such as ice cream, and the column that coincides with another measure, such as happiness. The correlation is the first number in this cell, 0.579 or 0.58. The correlation is labelled as Pearson correlation because, to confuse matters, researchers have invented other kinds of correlations, kinds that are not used as frequently. Most of the other numbers in this table are redundant or unhelpful, but one number is very informative. The second number in this cell, 0.001. This number is sometimes called the significance value or p-value. So what is the significance value or p-value? That is, what does p indicate besides a functioning bladder? To answer this question in detail, I would need to present a long, tedious answer. Now, I'm not too concerned about boring you, I'm just concerned about boring myself. So instead, at this stage, I'll present a rough answer and expand on this notion of a significance value or p-value later. To introduce this concept, we need to appreciate that if we had surveyed the entire population, such as every adult in this nation, the circumstances might be different. First, we would be more likely to experience a headache. But second, and more importantly, the correlation we generate might be different. The correlation might not be 0.58. Instead, the correlation could be 0.20, or indeed the correlation might even be 0 or negative. In essence, this significance or p-value offers some insight into whether, in the population, this correlation would be positive. That is, if this significance or p-value is lower than 0.05, we can be at least 95% sure this correlation actually differs from 0 in the population. In contrast, if this significance or p-value is greater than 0.05, we can't be 95% sure this correlation actually differs from 0 in the population. In this example, the p-value is less than 0.05. We can thus be 95% certain or more this correlation differs from 0 in the population. Specifically in statistical lingo, we conclude the positive correlation between ice cream consumption and happiness is indeed significant. You probably now feel quite excited, not because you've learned about correlations or p-values, but because the data seem to indicate that consumption of ice cream enhances happiness. You can now justify your inclination to dedicate your life to eating more ice cream. Unfortunately, the results don't necessarily indicate that ice cream consumption actually enhances happiness. Instead, two alternative accounts could explain these results, called the direction of causality and spurious variables. First, these results could be ascribed to what scholars call the reverse direction of causality. In particular, happiness might promote ice cream consumption rather than vice versa.
Can you think of why happiness could promote ice cream consumption? Perhaps when people feel very happy, they're not as wary or cautious. They're not as likely to worry about the health effects of excessive ice cream. In contrast, when people don't feel happy at all, they are more wary. They worry that excessive ice cream might be harmful. In other words, as many researchers like to repeat, a correlation does not imply causation. That is, a correlation between ice cream consumption and happiness doesn't imply that ice cream consumption causes happiness. People often repeat this phrase, the correlation does not imply causation. They like this phrase because the words sort of rhyme, and they like anything that rhymes. They probably regard Dr. Seuss as some sort of spiritual guru, but unlike other religions, rather than avoid ham, they eat ham with green eggs. Anyway, besides the reverse direction of causality, another account could explain this correlation. In particular, perhaps another trait or characteristic called a spurious variable may affect both measures, generating a misleading relationship. So to illustrate, perhaps wealthy people tend to consume more ice cream because they can afford this product, and perhaps wealthy people tend to be happier because they can buy anything they need. Therefore, a subset of participants, that is the wealthy individuals, might consume excessive ice cream and often feel happy. So researchers might assume that ice cream consumption and happiness are related to each other, as the following data seem to indicate. However, when you scan the responses of only wealthy people, or only the poorer people, this relationship between ice cream consumption and happiness is not as pronounced. The higher values in one column don't obviously coincide with the higher values in the other column. These results indicate that ice cream consumption might not enhance happiness. After you control wealth, that is, after you restrict your attention to people who are equivalent on wealth, ice cream consumption seems unrelated to happiness. Instead, the correlation we generated earlier can be ascribed to the notion that some other spurious variable, wealth for example, affects both ice cream consumption and happiness. And of course, spurious sounds a bit like spew. And just like spew can ruin nice carpet, spurious variables can ruin a nice study. To test the possibility that ice cream consumption is unrelated to happiness after wealth is controlled, add another column or variable to represent the income of each person. You don't need to copy these numbers exactly. Then add another column or variable to indicate whether this person is wealthy or not. Now we will attempt a procedure that enables us to examine the correlation between ice cream consumption and happiness in wealthy people, labelled 1 in this data file, and poorer people, labelled 0 in this data file, separately. In particular, select the data menu and then split file, the third option from the bottom, to generate this screen. Choose Organise Output by Groups and then transfer wealth to the box labelled Groups Based On. Then press OK. After you select these choices, subsequent analysis will be conducted for the wealthy participants and the poorer participants separately. To illustrate, calculate the correlation between ice cream consumption and happiness by, for example, choosing the Analyze menu, Correlate, and then Bivariate as before. And then press OK to generate the correlations. Now the output is exciting because the only experience that's better than one table of correlations is two tables of correlations. The first table corresponds to only the poorer people, labelled as 0. The second table corresponds to only the wealthier people, labelled as 1. But both these correlations are low, that is, the significance or p-values of both correlations is greater than 0.05. Therefore, we can't be 95% sure that either of these correlations would differ from 0 in the population. In other words, neither of these correlations differ significantly from 0. Now, before you proceed, you need to deactivate this split file option. In particular, select the data menu and then split file again. Choose Analyze All Cases, Do Not Create Groups, and then press OK. So far, if you told other researchers about all the topics we've discussed, scatterplots and correlations, for example, they would not be especially impressed. They would probably not fall off their chair unless their chair was very small and they were very large. But this next illustration revolves around a more impressive principle, sometimes called statistical control. Before we explain this principle, simply follow these instructions. Choose the Analyze menu, then Correlate, and finally Partial, rather than Bivariate, to generate this screen. As before, transfer ice cream and happiness into the box called Variables. Of course, I mean transfer the labels into this box. Don't actually pour ice cream onto your computer screens. That would be a waste of good ice cream. Then transfer the label Income into the box called Controlling For. Press OK. The correlation that appears this time is 0.08, a very low number. But what does this number indicate? Well, this number represents what the correlation between ice cream consumption and happiness would have been had everyone been average on income. Or in statistical lingo, this number represents what the correlation between ice cream consumption and happiness would be after controlling income. In this instance, had everyone been average in income, the correlation between ice cream consumption and happiness would be very low and not significantly different from zero. Actually, this technique, called a partial correlation, is really quite magical. I was going to show you how to cut a person in half, but I decided that this technique is much more magical. As this technique shows, statistical tests can be used to predict what the relationship between two variables, such as say ice cream consumption and happiness, would have been had everyone been average in income, even though not everyone was average in income. So the test can magically estimate what a relationship would have been in a hypothetical circumstance. Now, how SPSS performs this magic must await a further discussion, but it's an amazing technique nonetheless. Because this video has been so entertaining, I now want to briefly reiterate the highlights. The initial data implied that perhaps ice cream consumption could enhance happiness. But we then realised this pattern of data could be ascribed to alternative accounts. First, the data could be ascribed to the reverse direction of causality. And second, the data could be ascribed to a spurious variable, such as wealth. So, because of these alternative accounts, we can't justify our desire to bathe in rivers of ice cream yet. Fortunately, researchers have developed a design or approach that overcomes this problem and precludes these alternative accounts. For example, rather than survey 20 people, the researcher could have randomly assigned each participant into one of two conditions. Specifically, the researcher might, say, flip a coin, and if heads appears, the researcher would instruct the participant to consume ice cream every night for a week. And if tails appears, the researcher would instruct the participant to refrain from ice cream every night for a week. And the researcher would then repeat this procedure for every other participant. And a week later, the researcher would invite people to specify the extent to which they feel happy on a scale of 1 to 10. And when participants are randomly assigned to conditions, the design is called a randomized controlled trial, or sometimes just an experiment. And this table presents a subset of the results. The second bottom row specifies the average level of happiness in the people who consumed ice cream and the people who did not consume ice cream. In statistical lingo, this average is usually called the mean. Now, ironically, in everyday lingo, average usually means below average, like here's an average bowler. In contrast, in everyday lingo, mean usually means above average, like here's a mean bowler. But in statistical lingo, average and mean are synonymous. And these averages or means indicate that ice cream consumption enhances happiness. These results cannot be ascribed to the reverse direction of causality. That is, happiness could not have promoted ice cream consumption because only the researcher determined ice cream consumption. Likewise, the results cannot be ascribed to spurious variables like wealth. No spurious variable could have affected both ice cream consumption and happiness because, again, only the researcher determined ice cream consumption.
The bottom row represents another statistic called standard deviation. So what is this standard deviation? Well, this standard deviation is a statistic that represents the variability of these numbers in each condition. In this example, the happiness ratings of people who consumed ice cream are more variable, they're more different from one another than the happiness ratings of people who did not consume ice cream. Hence, the standard deviation is slightly higher in the ice cream condition than in the control condition. Although not strictly correct, the standard deviation is roughly the average extent to which each rating differs from the average or mean of that condition. So roughly speaking, on average, the happiness of each person who consumed ice cream differed by about 1.7 from that mean of 7.4. Likewise, on average, the happiness of each person who did not consume ice cream differed by about 1.4 from the mean of 2.4. To calculate these means and standard deviations in SPSS, you can apply several approaches. One useful approach is to construct tables. First, you need to construct another data file. In the File menu, choose New and then Data. Then enter these data and column labels. After you choose the Variable Views tab in the bottom left, shift your attention to the second last column called Measure. This column enables you to instruct SPSS that data for this variable are numbers, called scale, rankings, called order, or categories, called nominal. To illustrate, the column label condition actually comprises two categories: people who consumed the ice cream and people who did not consume the ice cream. Therefore, click the corresponding cell and choose nominal. In contrast, the column labelled happiness comprises numbers ranging from 1 to 10. Therefore, click the corresponding cell and choose scale. Now, whether you choose scale, ordinal, or nominal is relevant only to a few analyses or displays, and in general is not important in SPSS. Now shift your attention to another column called values. Now, this column is not related to your values, and thus is not an opportunity to tell the computer the extent to which you value, for example, world peace. Even the computer probably won't believe you. Instead, this column is an opportunity to label the two conditions. In the data view, we label the two conditions with the numbers 1 and 0. We can now inform the computer that 1 corresponds to maybe the treatment condition, that is, the consumption of ice cream, and 0 corresponds to the control condition, that is, the avoidance of ice cream. So click the cell in this column that corresponds to the condition variable, and then click the 3 dots to generate this screen. Then enter 1 in the box called Value and Treatment Condition in the box called Label before pressing Add. Similarly, next enter 0 in the box called Value and Control Condition in the box called Label before pressing Add again. And finally press OK. Then to generate the mean and standard deviation of each condition, choose the Analyze menu, then Tables, an option near the top, and finally Custom Tables to generate this set of options. Now, occasionally you might first receive a warning like, for optimal use of this dialog, value labels should be defined. Now, treat these warnings like you would respond to a parent who says, don't go outside with wet hair or you'll catch a cold. Just press OK and continue anyway. Click the cursor onto a categorical variable, in this instance condition. And before releasing this click, drag the categorical variable to the horizontal bar on the top called columns to generate this outcome. Now click the cursor onto a numeric variable, in this instance happiness, and drag this variable to the vertical bar called rows to generate this outcome. And these procedures will seem more intuitive later. Now click the button Summary Statistics. A button appears in the bottom left to generate this set of options. Drag down the dark blue bar to expose the entire list. And you can now choose other statistics such as standard deviation before pressing the right arrow. then click Apply to Selection, Close, and finally OK to generate the following table. This table presents the mean and standard deviation of each condition. The results merely indicate the average or mean level of happiness differs between the two conditions in this particular sample of participants. If everyone in the population, such as every adult in Australia, had participated in this study, the results might be different. Perhaps happiness would not differ between the people who consumed ice cream and the people who did not consume ice cream. Fortunately, researchers have invented a statistical technique to estimate the likelihood that happiness would have differed between the two conditions in the entire population. This technique is called an independent t-test, and this test is very popular. This person, for example, has just learnt about t-tests, and this person even named himself after t-tests. To introduce you to the t-test, simply follow these instructions. Choose the Analyze menu, then Compare Means, somewhat near the top of this list, and finally Independent Samples t-test to generate this set of options. Now for this analysis, the test variable refers to the outcome measure, happiness in this example. Therefore, click Happiness and press the top arrow to transfer this label into the box called Test Variable. The grouping variable refers to the two conditions. Therefore, click Condition and press the other arrow to transfer this label into the box called Grouping Variable. In addition, press Define Groups here to generate this screen. Enter 0 into one box and 1 into the other box to indicate that one group, comprising the participants who did not consume ice cream, was labelled as 0, and the other group, comprising participants who did consume ice cream, were labelled as 1. Then press Continue and finally OK to generate the following output. Now, a whole raft of confusing numbers seems to appear, but this time locate only the significance value or p-value associated with the t-value here. If this p-value is less than 0.05, we're at least 95% sure the two conditions would differ on happiness in the population. We would thus conclude that ice cream consumption significantly affects happiness. If this p-value is greater than 0.05, we are less than 95% sure the two conditions would differ on happiness in this population. We would thus conclude, in statistical lingo, that ice cream consumption does not significantly affect happiness. In this example, the p-value is less than 0.05, so we conclude that ice cream consumption significantly affects happiness. In other words, happiness would differ between the two conditions in this population. Now, you might be interested in why a very low p-value implies a difference between conditions would extend to the population. Well, roughly, this p-value is the probability these means would be so different if ice cream consumption doesn't really affect happiness. So a low p-value, below 0.05, indicates the probability these means will be so different if ice cream consumption does not really affect happiness in the population is very low. It's less than 0.05 or 5%. So consequently, ice cream consumption probably does affect happiness in the population. So far you've learned about two vital statistical techniques, correlations and t-tests. Now, to become experts, you need to learn about a couple of other techniques such as ANOVAs, ANCOVAs, MANOVAs, discriminant function analysis, chi-square test of independence, ranking test, linear regression, logistic regression, multinomial regression, Cox regression, multi-level modelling, generalised estimating equations, generalised additive models, cluster analysis, factor analysis, structural equation modelling, neural networks, decision trees, random forests, support vector machines, Riemann models, Fourier transforms, Bayesian statistics, and a few thousand other techniques and approaches. Now, to learn about all, say, 4,317 methods, you can press this button here, and absolutely nothing will happen. Instead, I'll show you how you can decide which techniques to utilise, at least in particular circumstances. For example, whenever you want to compare groups, such as males with females or people who consume ice cream with people who don't consume ice cream on some measure, you'll often conduct one of these techniques. To illustrate, suppose you want to examine the happiness of 10 participants before and then after they consume ice cream. So in this instance, you want to compare only two conditions or groups: before people consume ice cream and after people consume ice cream. Now, as the first column of numbers shows here, only 7 techniques are suitable when you want to compare only two conditions or groups. Second, you want to examine only one grouping variable, time, rather than say two or more grouping variables such as time and gender. Third, the groups are referred to as repeated measures in this case. That is, in this design, the same 10 participants are assigned to both groups, before and after. Now, only 3 of the remaining techniques are suitable to repeated measures, situations when the same participants are assessed more than once. Fourth, the outcome measure, happiness in this case, is numerical rather than categorical. That is, each person is assigned a number, such as 4, rather than a category, such as a black hair colour. Only one test is thus applicable in this circumstance, a paired samples t-test. Although a very brief demonstration, this illustration should offer you some insight into how to decide between these various alternatives. Of course, after you decide which statistical technique to conduct, you should probably not celebrate too vigorously for 2 reasons. First, you might hurt yourself. Hospital corridors are often crowded with research students splattered with blood after high-fiving a colleague upon realising they need to conduct a logistic regression. Second, you still need to actually conduct this technique. Fortunately, most statistical techniques are not too hard to conduct, and many resources at the university or videos on YouTube can be consulted to learn how to undertake this analysis. To illustrate, suppose you want to measure the happiness of, say, 20 people one day before, one day after, and 100 days after they consume a tub of ice cream. You also want to assess whether the effect of ice cream on happiness differs between males and females. Now, the data appear in this table, and you might want to construct a similar data file. To decide which test to conduct, you should recognise your design actually comprises 2 grouping variables: time, as in one day before, one day after, and 100 days after consuming ice cream, as well as gender, as in males and females. Hence, only these analyses could be applicable. Furthermore, at least one of the grouping variables is repeated. That is, it's the same participants are measured one day before, one day after, and 100 days after consuming ice cream. Therefore, according to this table, we need to utilise a mixed model ANOVA. Now, specifically, because the design comprises 2 grouping variables, time and gender, the technique is also called a 2-way mixed model ANOVA. And if the design comprised 3 grouping variables, the technique will be called a 3-way ANOVA. And if the design comprised 100 grouping variables, well, then you've probably lost your mind. Anyway, to be honest, the table is not quite accurate. This technique is called a mixed model ANOVA if one grouping variable is repeated measures, such as time in this example, and the other grouping variable is not repeated measures, such as gender in this example. That is, the males and female groups comprise different people, so gender is not repeated measures. In contrast, this technique would be called a repeated measures ANOVA if both grouping variables were repeated measures. But let us overlook this complication for now and instead proceed with this technique. So how do we conduct this mixed model ANOVA? And what the hell is a mixed model ANOVA? Well, ANOVA is an abbreviation of analysis of variance, a term that's just as meaningless really. In essence, ANOVAs compare more than 2 groups on some numeric variable. And a mixed model ANOVA merely indicates that at least one of the grouping variables is repeated measures and at least one grouping variable is not repeated measures. Now, to conduct any ANOVA, choose the Analyze menu
and then General Linear Model, an option that appears somewhat near the top. To conduct an ANOVA with one or more repeated measures variables, such as time, choose then the Repeated Measures option to generate this screen. First, you need to inform SPSS that one of your grouping variables is repeated measures. That is, until you complete this procedure, SPSS would not be aware that 3 of your columns, that is, before, 1 day after, and 100 days after consuming ice cream, actually represent 3 different times that you want to compare. So in the box just below, within subject factor name, enter a name for your repeated measures variable, such as time. Now within subject is merely another term for repeated measures, and factor name is merely another term for this grouping variable, and confusing is merely another term for what you're probably feeling now while you're inundated with these terms. In the box labelled number of levels, specify 3 to differentiate the 3 categories of time: 1 day before, 1 day after, and 100 days after consuming ice cream. And number of levels is another term for sort of number of categories in one variable. And then press Add, and then that Define button to generate the next screen. Now in this screen, in the box called Within Subject Variables, transfer the 3 times, that is 1 day before, 1 day after, and 100 days after, respectively, to this box. So this box informs SPSS that 1 day before is the first level or category of time, 1 day after is the second level or category of time, and 100 days after is the third level or category of time. In the box called Between Subject Factors, specify gender. Now, between subject is merely just another term for not repeated measures. Now, press OK to generate all these tables of output. Now, the key tables that you need to focus on are called test of within subject effects and test of between subject effects. So how do you interpret this output? Well, we primarily need to interpret just 3 key numbers. First, this highlighted number indicates the significance or p-value associated with time, and in this case is less than 0.05. So therefore time is significant. So hence we conclude that happiness varied across the 3 times. Now if we computed the average of each time, we could then determine whether happiness increased or decreased across these times. Second, this highlighted number indicates that the significance or p-value associated with gender is greater than 0.05. Therefore, gender is not significant. So hence, we conclude that happiness does not differ between males and females. And third, and most interestingly, this highlighted number is also greater than 0.05 and thus not significant. But what does this row refer to? What does the symbol time * gender mean? Well, this symbol refers to something called the interaction, in this case between time and gender. But rather than define this interaction, I'll demonstrate how you would interpret this number. Because the significance value or p-value is greater than 0.05, we will conclude in this case that the effect of time on happiness does not differ between the genders. That is, the change of happiness over time is the same for males and for females. In contrast, if the significance value or p-value had been less than 0.05, we would conclude that the effect of time on happiness actually differs between the genders. For example, happiness might, say, improve across the 3 times in males, but diminish across the 3 times in females. Now finally, you might notice that for each effect, SPSS did not report only one significance or p-value. Instead, for each effect, SPSS reported 4 of these p-values. So why did SPSS report 4 p-values? Well, to partly answer this question, statistical tests are only accurate when the data fulfills particular characteristics or patterns called assumptions or statistical assumptions. If one of these assumptions is violated,